Okay, so we've talked a lot about forces, but there's actually two kinds of forces. One is a conservative force and one's a non-conservative force. So a conservative force is something like the force of gravity. And gravity, we know, has a potential, right? There's a gravitational potential. Also, there's the force from a spring. And we learned in the last class that there's also a potential for a spring. So for any conservative force, there's a potential, and the potential is a function of position. So you can figure out how much potential there is just by looking at where the object is. So for example, for gravity, if I take my phone and I lift it up higher, then the gravitational potential is just defined by where it is. Or if there's a spring attached to this and it's like attached on the side, and then I move it and stretch the spring, then just based on how far it's displaced from its equilibrium, you know how much potential energy is in that spring. So just from the position, you can figure out how much energy there is. Now, there are forces that don't have that feature. Things like friction. Right? Friction is a non-conservative force. Or pull, or tension, or normal, or drag. So all of these are non-conservative forces because there isn't a potential, something that tells you if the object's here, that's how much potential energy it has. And so those are non-conservative forces. So in the previous video, we figured out the work done by the force of gravity is equal to minus the change in the potential. So it turns out that that's true also for spring or any conservative force. You'll be able to write the force as negative the change in the potential. My first question is, if an object moves a distance d and then comes back to where it started, so we take my phone, move it up here, and then we move it back to where it started, can we show that the work done by a conservative force has to be zero? So my question to you is, if we have an object like my phone, and we start in one place, and then bring it somewhere else, and then bring it back to the original place, can we show that the work done by gravity, or a conservative force in general, is zero? So the answer is yes, and I will show you how. So for example, the work done by gravity is equal, as we said, to minus the change in the potential, which is u, so it's minus u final minus u initial, right? So, or u initial minus u final. But these are both in the same position. So these are both u of, if we call this position x naught, then this is the initial potential is u of x naught minus the final, which is u of x naught. They're the same thing, so they cancel out, and we get 0. And so if you have something that moves away and then back to the same place, then the conservative forces will always sum up to 0. So my second question is, if we're now thinking about non-conservative forces, we have an object, we move it somewhere, and then we move it back, can we prove that the non-conservative forces can be non-zero? So we don't get 0 like we did for the conservative forces. So let's start out by looking at the mechanical energy. So we know that the mechanical energy is equal to the change in the kinetic plus the change in the potential, right? So I'm going to do a little math here, but then we'll get to this conclusion that we want. So one thing that you probably read from the pre-reading is that the change in the kinetic energy is equal to the total work, the work net, or that's equal to the sum of all the work, basically the work from each force, so we'll basically sum over the forces, on a particular object. But there's two kinds of work, like I was saying. We have the work conservative plus the work non-conservative, right? And then there's something else that we just learned, which is that delta U is equal to minus the work conservative. So we can plug both of these into this equation, and what we get is that the change in the kinetic energy is the work conservative plus the work non-conservative, and then delta U is going to be minus work conservative. These two cancel, and we just get the work non-conservative. So what this is saying is that the change in the mechanical energy is equal to the non-conservative work. So, for example, if I take my phone, okay, let's first think about an example where I don't have it end up in the same location. So if I take my phone and I bring it up here, the change in mechanical energy is going to not be zero because the potential energy has changed, even though the kinetic energy didn't change, 0, 0, at rest, but the potential energy changed. So there was some non-conservative work to bring my phone up here, and that was the non-conservative work that I used to push it up there with my hand. Now, you can also have non-conservative work that's non-zero if something comes to the same place. So what's an example of this? Okay, so what if we take my phone, we have it in this location, I move it somewhere else, and then I bring it back and have it moving, so when it gets back to the same location, it's moving. So what that means is that the potential energy was the same, but the kinetic energy is different even though it ended up at the same location. So since the kinetic energy changed, that means that our mechanical energy is non-zero because the initial velocity was 0 and the final velocity was non-zero. And if this was non-zero and it's equal to the non-conservative work, then that means the non-conservative work was also not 0. So that's just a little bit about conservative work and non-conservative work, and I hope that helps.